a good set of people here. And as before, if you want to, if you are right now listed as an attendee and you would like to be able to unmute yourself and ask questions, just raise your Zoom hand and you can be promoted to a panelist. And yeah, it would be great if more people ask questions, more people turn on the cameras. So please feel welcome to do it. And with that, uh, and with that, let's start Ayush's talk, part three of this three-part series. Thank you.
So first of all, thank you, Boaz, and the organizers for making this wonderful program. So let me now jump straight into where we left from. So from Rachel's talk and Amit's talk, both of them did a wonderful job at motivating that in order to build obfuscation, it just suffices to build a seemingly much simpler cryptographic primitive that is a weakly secure structured seed PRG, which I'm going to just focus on for this talk and tell you how we can construct it from PRGs in NC0 and LPN. And what's nice about just focusing on this standalone problem is that even if you missed the previous two talks, and if you're just tuning right now, if you just believe me for the time being that in order to build IO, it suffices to just focus on this object, then hopefully the rest of this talk should be understandable. Throughout this talk, I'm just going to use combinatorial and elementary ideas. I'm not going to assume too much of a crypto background. And if there are any questions, just interrupt and ask. So let me start off by recalling one of the two main assumptions, the learning parity with noise. So just going to be a very brief recall, because we saw this in detail in Amit's talk, and we're also going to hear about it in Benny's talk. So just from the sake of setting up notations, what does learning parity with noise assumption says? It says that there are two distributions that are indistinguishable. In the first distribution, I'm going to have noisy linear equations. Now, how are they sampled? So there's a field ZP, and I'm going to sample n vectors. So n is polynomial in L, n vectors at random from ZP to the L, and I'm going to denote by AI. Then I'm sampling a secret S at random from ZP to the L again. Then I'm going to compute these inner products AI and S. And then I'm going to perturb these inner products with a sparse noise. Now, how is this noise chosen? It's going to be 0 with a large probability. So it's really sparse. However, with tiny probability, that is L to the minus delta, where L is the dimension, and delta is some fixed constant, fixed once and for all, between 0 and 1. With that probability, I'm going to choose it at random, and then I'm going to perturb with that noise. So then I have these noisy linear equations, and I hand it out to this adversary. And this LPN assumption says that AIS plus EI, this distribution looks computationally indistinguishable to AI comma uniform. Okay, so that's the variant we are using. And as you can see, when delta increases, becomes closer to 1, this problem becomes easier and easier. When delta is closer to 0, this problem becomes harder and harder. And just for the sake of concreteness, we are going to work with delta, which is an arbitrarily small constant. So even if this assumption holds for delta equal to 0.0001, that's already enough for us to get to IO. So that's our first assumption. The second assumption we are making is existence of Boolean PRGs in NC0. I'm sure all of you know what PRGs are. They are length expanding Boolean functions. They take n bits as input, and then they output m bits. Really think of m as some polynomial in n, so n to the 1 plus constant. We are looking for PRGs evaluatable by constant depth Boolean circuits, so NC0. And this has this traditional conventional notion of security that you hear in cryptography, the notion of pseudo-randomness. What does it say? It says that when x is chosen at random from 0, 1 to the n, then the output g of x should look computationally indistinguishable to a random string of length m. So that's your security. And this is PRGs in NC0. This has been reasonably well studied. There has been 20 years of work. But that's not my job for today. I'm going to let Benny discuss history about it. Benny is an expert on PRGs in NC0, so I'm going to let him speak about that. Uh, I'm going to just tell you about two facts which I'm going to use in the construction. So these facts are kind of somewhat important. So I'll demand your attention here. When I talk about any NC0 function and therefore any PRG in NC0, it has a constant locality. What do I mean by that? I mean that if I look at the output, which is an m-bit string, every output bit is going to depend on at most a constant number of input bits. So that's just the fact of locality being constant. An immediate fallout of that is that you can write every output bit yi as some constant degree multivariate polynomial over the reals, treating input as the variables. And in fact, this polynomial has integer coefficients. Okay, so this is just an immediate fallout of that. And I'm going to use this fact later on this talk. So if you have any questions about that, just please feel free to ask me. And just to give you a sense of what parameters we are using, we are going to work with a PRG with a stretch of n to the 1 plus tau. So m is exactly n to the 1 plus tau, where tau is an arbitrarily small constant greater than 0. So even if this assumption holds, meaning that there exists a PRG in NC0 with a stretch of n to the 1.001, that's already enough. So with that in mind, with all these definitions in mind, let's just get straight to business. What is
Aayush,
a
sorry,
sure,
can I ask a quick question?
sure.
Is there a connection between the constant here and the epsilon delta that we heard about from the LPN assumption? I mean, are they all free constants, or do they need to be related in some way?
They're all free.
Okay,
They don't depend on each other. Like you can,
thanks.
yeah. Okay. So what is a structured seed PRG? We have seen this definition informally in Rachel's talk, almost formally in Rachel's talk, and in Amit's talk. So let's dive deep into this in here with formal definition. Roughly, they are PRGs which are computable by bilinear map, so they are bilinear map friendly. And this definition is implicit, in fact, in previous works. However, it's just formalized in this current work. What does it say? So we are really asking for a PRG which has a structured seed, which has a special structure. Now, in a traditional PRG, you would think of the seed or the input being a random string over the hypercube. Here, you are asking that the seed is kind of fragmented, like there are two components in the seed, which I'll denote as the public part of the seed and the secret part of the seed. So the public part of the seed is actually just leaked out to the adversary. It's given in the clear. Secret part of the seed is hidden. And what we demand is that think of these seeds, public and secret, as being vectors over ZP. So P is looking ahead and connecting the dot. P is the order of the bilinear map that we're going to use. So you're asking for these seeds to live in ZP to the K. They might be arbitrarily correlated. There is no restriction on that. They might be arbitrarily structured. They don't have to be uniform and all that. Only thing is that they are efficiently sampleable by some polynomial time algorithm. Okay. Now, this is how the seed looks like. And when it comes to output, you're asking that each output bit can be written as some constant degree polynomial on the public part of the seed and the secret part of the seed, with a restriction that it is just degree 2 over the secret part of the seed, mod p. So this polynomial is over ZP. So it's the fact that it's a degree 2 over the secret part of the seed, roughly it's coming from the fact that we are going to use bilinear maps, and remember bilinear maps only let you do up to a degree 2 computation over the secrets. So that's the restriction where it's coming from. And then we're asking some standard properties. First property is the stretch. The number of output bits, they should be much more than, in fact, some small polynomial in the size of the public part of the seed plus secret part of the seed. So the total seed length. So that's just an extension of the expansion requirement of a regular PRG. Now, security is also a straightforward generalization of a regular PRG, just adaptation. You're also going to leak the public part of the seed. So given that, the output y should appear pseudo-random. So p comma y should be computationally indistinguishable to p comma random string of length m. That's also a straightforward generalization of regular PRG definition. So that's what I hope the goal is clear. What are we trying to build? And if there are questions, please interrupt me right now. Okay, I'll assume that there are no questions. So that's what we are trying to build. Now, a reasonable question that you might ask is, why are we considering this model at all? Did it not suffice to just think of PRGs, which are just degree 2 functions over a single secret seed. And why was this introduction of public seed necessary? Um, well, turns out that's what we considered. We considered PRGs. There's just one seed, and the output was a degree 2 polynomial. In a number of works, we considered it, and unfortunately, what happened is that all of those proposals were broken down in a series of devastating attacks. So there was this really nice line of work by Barak et al., Lombardi and Vekunathan, and Barak et al. Again, which showed implausibility results. They are implausibility results because they don't rule out all generality of parameters and candidates. They just do it enough so that our confidence is like shaken in this whole paradigm. And what they use different ideas, but the unifying feature in all these works was that they relied on a really powerful hierarchy of convex optimization known as the sum of squares hierarchy. And if you're aware, sum of squares is known to yield some of the best known approximation algorithm for some really hard problems, including the max cut problem. So all of them relies on sum of squares. Unfortunately, I won't speak about it too much in the interest of time. The only thing I would say that the takeaway from all this was that you want to avoid um, using PRGs, which are just degree 2 computations. That's what you want to avoid. And I remember when all these attacks came out, this was really disappointing in the sense that this was another paradigm which was broken down over the past, like, in a quick section of time. And there was a general pessimism when this happened. However, still we are really, really thankful that this happened because this kind of forced us to consider this new model of this public seed. There was no other choice. We had to consider a PRG where there's this extension that we are considering. So we're really thankful to all the people who worked on it and sum of squares in general. So thank you for doing that. I would have loved to talk more about it, but unfortunately I can't. So I'm happy to talk about it offline.
Ayush, I have a doubt.
Sure.
So, since in the security game you are giving P in the clear, it's not
Yep.
completely clear to me how this is really different from degree 2 computation. I mean, I don't know if this was discussed already,
This
but
was discussed in Rachel's talk, but that's fine.
could you repeat the
Yeah,
argument?
yeah, yeah. I can repeat the argument. So the point is this. So you're asking essentially if you could sample this P uniformly and fix it in the CRS, right? Is that what you're
Yes,
asking?
yes, yeah, yeah, yeah.
Yeah, but the point is that the secret part of the seed will actually depend on this public part of the seed. Like there will be correlation, and if you just give it out in CRS, then it's actually useless. You're not.
So you're saying the key S and P, it's not necessarily that P and S are chosen independent of one another. It's
They're
like
not
P is.
independent. In fact, that's very crucial. They are correlated in some way, in computationally hidden way. So if someone just looks at P, they won't be able to tell what's the secret S. But there's like some computationally hard correlation between them, which is chosen
So,
at sampling.
so this is still a stronger requirement, right? Because you are saying you're really revealing something about S in the form of P, and still it shouldn't be able. It shouldn't
And he should be
able to.
able to come up with the secret. Yes, that's exactly what we're saying.
Okay. Okay. Thank you.
Okay, so let's proceed. Now, what's the goal? How do we construct this? So I hope you're convinced that this considering this model was somewhat necessary. So now let's see how you construct. How can you construct it? So what's the goal? Ideally, if everything worked out for us beautifully, we would have wanted our input to sit in a Boolean hypercube, like a random input, and the output should look like a nice evaluation, like PRG in NC0 G evaluated at sigma, which is like an n to the 1 plus tau bit output. That's what we have ideally wanted. But what's the problem? The problem is that we do not know a PRG in degree 2. I mean, all these attacks, in fact, point otherwise. So this is not a degree 2 computation. We have to go at least degree 3. So this you cannot do. But what we realize is that if we are willing to use this model, I'm going to set this public seed very cleverly. I'm going to set this public part of the seed as some LPN samples encrypting the input sigma. So let's see how they are sampled. This is somewhat important, so I need your attention here. So if your input was n bits, I'm going to generate n samples. How are they sampled? Well, there are coefficient vectors ai which are chosen from ZP to the L. Then there is a secret S which is chosen from ZP to the L. So I'm going to compute this AI and S. Then I'm going to choose an error. This is chosen according to an LPN error distribution. So it's a sparse error. So it's non-zero only with a probability L to the minus delta. Then I'm going to add it and then use this LPN sample to encrypt sigma. So just add sigma into this. So there are n LPN samples encrypting sigma. So that's how we compute this public seed. The point, if we are willing to give out these public information, then I can come up with a really short seed, not really short, but somewhat short seed, private seed S. And this private seed is going to only depend on two things. So it's going to depend on the secret S. So remember, our secret of the LPN is much smaller than the number of samples. So it's going to depend on that. And then it's also going to depend on the sparse error vector E. Okay, so I compute some information. I'm going to tell you exactly what this is, but just assume that it is short, such that the size of public seed plus size of the secret seed is much smaller than M. And then what it lets you do magically, what we show in this work, is that you can write each output bit of the PRG as some constant degree polynomial over P and S, with the restriction that it's just degree 2 over the secret. Okay, the exact complexity model that we require. Okay, so once we have this, and let's say we are also able to argue security, then as Rachel said, we are golden because we can get IO using the same bootstrapping. So only thing I need to tell you about now is how do I evaluate it and what's the security. Turns out security is an embarrassingly simple argument. So Amit talked about it in his talk. So therefore, I won't spend too much time. If time permits, I will give you it formally, but roughly the main idea is that all adversary gets to see is the PRG evaluated at sigma, and these LPN samples encrypting sigma. Remember, these are LPN samples which encrypt sigma, so they are hiding the seed sigma. And then since the sigma is hidden, then G of sigma appears pseudo-random. That's the whole argument. So that's the security proof. So more interesting piece that remains is that how does our private seed look like, and how we actually evaluate it using constant degree polynomial. So I hope the goal is clear. So if there are questions, please let me know.
So just to make sure that, so what's the, so I'm just a little bit confused on what do we think of sigma? Do we think of it as a part of the private seed or not part of the private seed?
No, it won't. The private seed will just be a function of S. Actually, it will depend on sigma, but only like implicitly. So yeah, I mean, it will depend, but I'm going to tell you exactly how it depends. In general, private seed is allowed to depend on everything, all randomness that you use to sample P.
I see. Okay. So okay. So the private, okay. So we are not directly operating on sigma, but rather we are going to produce the output that we are going to produce the output that we see on the right hand side by doing some calculation that will be only degree 2 in S and constant degree in capital P, right?
Exactly right. But only restriction we want is that the sampling algorithm has to be efficiently samplable private seed and the public seed. But otherwise, this private seed can depend in any crazy fashion on all the randomness used to sample public seed.
And again, just to get kind of a sense, S and E right now are much smaller. Could put okay, so maybe E not. So S at least could be much smaller than potentially than M. It could be a small power of M, right?
Yeah, it's in fact much smaller than N, which is the number of samples or the number of inputs. But E is not smaller than N, but sorry, the E is a sparse vector, so it will also be like L to the minus delta fraction of the total length of N.
I see, and this is
that's crucial.
We need to talk a little bit about encoding at some point.
Yeah, and then that's what I'm going to talk about next.
Okay.
So you still didn't tell us why you need the sparsity, right? Of E.
Yeah, I haven't. I'm just giving you the intuition that.
Yeah. Okay. This is okay.
Sure.
So maybe I missed it, but I'm not sure that I fully understand the syntax of this object. Like the way that I understand it right now, maybe there's a different way to define it. You have a sampling, like a sampling algorithm that samples the output, but it also samples basically the private seed, like I don't know, like some sort of alternative seed in a public part, such that given these things, this is kind of the preprocessing. Given these things, you can compute the public output in a degree 2 thing via degree 2 mapping. That's the way to think about it.
Yeah, exactly. So you have a desired output G of sigma, which is what you want to compute. Now there is a algorithm that will run in. So let's say the running time of that is like the length of the PRG is m. In a traditional PRG, you would think of seed sampling algorithm should be much independent of m. In this case, however, the seed sampling algorithm can take time which is proportional to m, like crazy polynomial amount of time, which kind of compresses this output in this way. Like it's going to encode the seed of the PRG using this LPN samples and then come up with this preprocessing, which computing this preprocessing actually takes a lot of time. But the only restriction is that it's short. That's the only restriction we need.
So it's not the case that you can generate a seed, do this kind of degree 2, like a random seed, apply a degree 2.5 computation on it and generate the output. This is not the case, right? Because this is also related to Amit's question before.
Yeah, exactly. The private part of the seed will depend on G of sigma.
Okay.
Private part of the seed.
Sorry, the private part of the seed. The private part of the seed will depend on
G of sigma.
Okay.
It will.
Okay, so I didn't get that. Okay, so basically, yes. So there are two ways to compute the output. One is the way you actually use, which basically you sample at random sigma, E, and S, and then obviously you can compute everything that is on the right box. And then there is an extra hypothetical way, which is if you found some magical way to sample G of sigma, capital P, and the preprocessing thing, then you can evaluate okay, so if you found G of sigma.
So yeah, you're right. Technically, I should have said it as like preprocessing of S, E, G of sigma, and sigma, basically everything.
Okay, or just sigma, maybe. Okay, or sigma,
yeah,
right?
Sure. Yeah, or sigma.
Okay. Okay. So maybe okay. So then maybe in principle you could compute. You could ignore the obvious way to compute. So one way to think about it is preprocessing is also a function of sigma, and what you do is you sample at random jointly capital S and capital P, and then there is a way to compute G according to a formula as written below, right?
Yeah. And we're going to
in this the only error really in this slide is that preprocessing is really also of sigma.
Yeah, it depends on all the randomness used to sample P and desired output.
So the preprocessing is basically giving you the key, the secret key, right?
Depends on the secret key, but it preprocesses it in a way that will allow you to only do degree 2 computation. So right, so it represents the secret key in a way that is more convenient to do calculation on.
And using binary maps, yes, and the fact it's short.
So do you think maybe you can think about it not necessarily as preprocessing, but as compression of the output of the PRG, right? So you evaluate the whole PRG and then you compress it into these seeds.
Right.
I can't hear.
Yeah, right. That's true. So you are saying the preprocessing depends on the description of G. Is that what you're saying?
Sorry, I couldn't hear you. Can you please repeat it? Yes, no, it's on my end.
I'm saying that. So you are saying preprocessing depends on the output, G of sigma.
Yeah.
That
kind of reminds me of the XIO that Yael was talking about, and we're going to hear about also tomorrow. In the sense where you have this notion of like, well, we can look at the whole thing, but then we need to come up with sort of a compact way of like a side conversation I was just having with Nico.
So you are saying more accurate term will be calling it compressing algorithm.
I'm just wondering because it seems like all of these ideas are kind of sort of boil down to similar
compressor.
outlines, right?
But I think there's something different here, that the compressed value is still secret, right? It's not like the compressed value is the public part.
Yeah, it's
You
always
still need this to be secret.
it's trivial to compress an output of a PRG to something secret. The seed is always a compression.
Yeah.
But so here it really is about the fact that the decompressing algorithm becomes
So-
0.5.
So in XIO, the compressed thing is also a public thing. It's the XIO obfuscation, right?
Right, there it's public, here it's secret.
Semi-secret, right? So you're saying, well, you're saying it doesn't even, all the compression doesn't even need to be public. It's okay that there's some part that remains secret. But you make it simpler. Okay. So right. So here there's another sort of axis of improvement, right? You make the function simpler by making part of it public and leaving part of it secret. Yeah, I don't know.
The fact that bilinear map is an obfuscation of degree 2 functions itself, so it gives you some power that you can hide some sort of secrets with a restriction that you can only do degree 2 computations on that.
I think that there's a big difference between having like a PRG which takes a uniform seed, applies say a degree 2.5 whatever and generates the output, versus the thing that you can generate pseudo-random strings, but then you can kind of generate synthetic seed. This is the thing that you generate, such that based on this synthetic seed you can evaluate a degree 2.5. That's what allows you to bypass the attacks, right? Otherwise, Amit's points would be valid, right? You could apply the attacks by just fixing the public part and look at it as a degree 2 computation. That's crucial.
Yeah, that's crucial.
Attacks work on attacks didn't need the attacks didn't need the seed to be uniform in any way. So
no, but the point is that it's not a degree 2 mapping, right? I mean, when you think about the seed as non-uniform, it means that you sample it by using something which is not a degree 2. There's a higher degree thing that is hidden there, right?
No, that still the attacks would still have worked even if you sample a seed. I mean, I think it is kind of crucial here that so it's not the same, right?
Yeah, the attack works as long as the public seed and private seed are independently sampled. It doesn't matter what's their individual distribution. As long as they're independently sampled, you can always fix the public seed. So what we really rely on is that they're correlated.
That's kind of crucial.
We're going to see the actual construction of
just next.
Yeah, now.
If we stop asking questions.
Sure. Let's just jump right into it. So what's the desiderata? Well, I've told you what the public seed looks like, AIS plus EI plus sigma. For sake of convenience, I'm going to put the coefficient vectors as a CRS, like it's known to everyone. And now your goal is to find a short seed, which lets me compute this way. So I hope that is clear. Now, my point is that just because we are encoding like this using LPN errors, half the battle is already won. Remember, our PRG is a PRG in NC0, so it's expressible as a low degree D polynomial over the reals, right? So let's see what we can do. So what I'm going to do, I'm going to first pre-compute all the monomials in the secret of the LPN of degree D over 2, at most degree D over 2. I'm going to compute all the monomials and put it in the private part of the seed. Now, a reasonable question to ask is, why can you do that? Like, won't it blow up the size? Well, I'm going to set the dimension, as Boaz was saying, I'm going to set the dimension of the secret small enough so that it's not too much. So the number of monomials will be something like n.
And 2 is not a magic thing here. I should just want to make sure that if you wanted to, maybe you don't need. If you wanted to, you could make it D.
Yes, you could have. You'll just get slightly worse parameters in the final construction. This is not where D or D by 2 is crucial. But let's say for the time being, just let's do all the monomials of degree D over 2. Now what you can do, you can do this. So you can compute this polynomial G, which is, I told you, it's a constant degree polynomial over the reals with integer coefficients. So I can also evaluate it mod P. I'm going to evaluate it at B minus AS. Okay. Now, why can I compute it in this complexity model, the degree 2.5 complexity model? Because this is a degree D function, therefore it's degree D in B, but B is public, so that's fine. It's degree D in A, so A is public, that's fine. It's degree D in S, but I have pre-processed all the monomials of degree D over 2 in the private seed. So it's degree 2 in private seed. So you can compute this. Now, here is the point. The point is B minus AS is just sigma plus E. Okay, the seed plus error, mod P, right? Now, just see essentially what are we doing? We are computing this PRG on an input, which is sigma on most of the places, but on a few places with like probability L to the minus delta, I have some corruption of the error, because remember E is a LPN error which is chosen, so it's a sparse error. So we are computing it at approximately the right input. And now you realize that PRGG is actually a constant locality PRG. The number of input bits that each output bit is affected by is just a constant. So therefore, I can compute that every output bit is desired output. So for every given I index, the computed output is actually equal to the desired output G of sigma. That's at least 1 minus 1 by L to the delta to the power locality, right? That's just a straightforward calculation using the probability of error from LPN. This comes out to be pretty large, 1 minus order of L to the minus delta. So what does it say? It says that any individual output is already correct with probability 1 minus a small fraction L to the minus delta. And now you can do some more refined calculations. So you can ask expectation. Turns out that the expected number of bad output bits. Now bad output bits are the output bits which are not correct, which are not equal to my desired computation. This is something like m by L to the delta. Okay, so a non-trivial fraction of those are bad, like just m by L to the delta. And then you can do Markov argument to show that the size of the bad set is lambda folds more than this expected value is less than 1 by lambda. Now, what does it say? It says that it's only with 1 by lambda probability, where lambda is this parameter, I'm going to have more errors than lambda m by L to the delta. But with very large probability, a probability of 1 minus 1 by lambda, I'm going to have errors fewer than m lambda by L to the delta. Okay. So this means that for the rest of the goal, what we can do, just focus on correcting m lambda by L to the delta errors without worrying about anything. Now there's a tiny chance, 1 by lambda chance, I will have more errors. In that case, we'll just give up and let security amplification take care of. We'll lose some security and that's fine. We know how to
just
do it.
to check, if EI is 0, you will get an error, right? Or is that not for sure?
If EI, okay, so look at each output bit, see how many, it depends on some sigma I plus EI. Now, if all the errors EIs are 0, then you will get the right output. If there is one of them which is non-zero, then you might get something else.
But they might cancel out occasionally.
Occasionally, but we can count on it.
Sure,
very, very tiny chance. Okay.
Thanks.
Okay, so m lambda by L to the delta.
Aayush, could you not have relied on some more independence here to actually say that this probability is negligible?
That's a good question. If we use a random hypergraph, like in typical PRGs, you will have a random hypergraph. I mean, then you could, right? Then you could show, in fact, that you can rely on some better concentration bounds, and then you'll be good. However, we don't want to make that restriction. We are working with arbitrary PRG in NC0, so we don't know how the graph is sampled.
Right, and you anyway lose this lambda from
exactly. We will also anyway lose it with 1 by lambda probability, as Boaz is saying. Like not all hypergraphs are good, but then we can rely on combining security or something else. So I mean, essentially, it's some loss somewhere.
But that's the only reason why you don't get a negligible security in your component. So in principle, if you were willing to assume some pseudo randomness properties of the hypergraph, then you would get negligible error.
Yes, that is correct. If you use a random hypergraph, you get like better bound here. Also, we could resample the seeds many times, but that requires a very careful analysis. So I'm not going to talk about that. There's a way to.
You could always apply the random hypergraph on your PRG, right? An arbitrary PRG, and make it robust in this sense, I think.
Say that again.
you can always plug in this random hypergraph over your PRG and argue that you don't lose security. It's not a new assumption, and you'll get some sort of robustness from the original PRG.
I see.
Just plug it in, wrap your
I see.
PRG with this extra layer of random hypergraph and apply XORs or whatever.
Okay, yeah, that'll be
I
interesting.
mean, I guess that there are many solutions.
Yeah, but say that, but resampling will definitely work. You can sample the seed many times.
We'll let Aayush. I will give you extra time, but
Sure.
still we'll let him continue.
Sure. Okay. Let's just assume that this is fine for now. This goal of correcting m lambda by delta errors. Okay. So what's the point? One naive approach is that what we want to do is the following. We define this correction vector, which is g of sigma minus g of sigma plus c. So this is the desired computation minus the actual computation. This is the error vector. Now somehow what I want to do, roughly the high level goal, I want to put it in the private part of the seed somehow and then compute this y prime as just the computed value plus the correction. So I'm just literally correcting the offset. But the point is we cannot just trivially do it, right? This correction vector is too big. The dimension of this is m. So all the stretch will be killed. So the point is that we need to somehow make use of the fact that this correction vector is sparse. Remember, the correction vector has m lambda by L to the delta entries. You got to make use of the fact. But we cannot just use it directly. One naive way of using the fact that correction vector is sparse is by only putting the non-zero values in the private part of the seed. That would have worked. We could have guaranteed expansion because this is non-zero only at m lambda by L to the delta points. But then the only way we know how to use this fact is like by revealing the indices of bad output bits, like the output bits which need correction. And then at least we could not figure out a way in which you'll not hurt security. So revealing the set of bad output bits is actually very like it hurts LPN security because you'll eventually leak which of the LPN samples have errors in them.
There is also, like Aayush, another thing you could potentially do, which is to also put the indices of these points as part of the private seed. That also would not cost much, but it will be a high degree computation.
It will be a high degree computation, exactly. So we couldn't figure out a way of making use of these ideas. So what is the high level picture then? What are we going to do in order to get around it? Roughly how our solution looks like is the following. We're going to take this correction vector and observe it's a really sparse vector. We're going to encode it in a matrix, in a big matrix. But this matrix is going to be sparse. And then every sparse matrix, like very sparse matrix have low rank. We'll use matrix factorization to compress it. That's all we are going to do. So let's see this with an example. Let's say you have one error. So let's say the correction vector just has one non-zero entry, and let's see how you can make this work. So remember, we have m output bits, so I can make a matrix of size root m cross root m. That's the dimension. This matrix has m entries. Then let's say I pick any obvious bijection which maps the output bits of the PRG into this grid. This is some obvious bijection. Like you could, I'm not specifying how to sample this. So what's the point? We'll take the correction vector. Remember, it is one sparse. And then I'm going to map it using this bijection into this grid. So m of phi I is correction of I. Okay, so just put it here. Now I observe this is a rank 1 matrix. I can factor it as u times v, where dimension of u and v is root m. So this is just because it's rank 1 and the width of the matrix is root m. Now it's straightforward. I'm going to put this u and v in the private part of the seed, and I'm going to put this index phi in so that it's publicly known. Then I'm going to compute the following: g of sigma plus c, that was what I was already computing, plus I'm going to construct this correction matrix reconstructed by multiplying u with v. So it's a degree 2 computation, and that's legit because we could handle degree 2 computation in the secret part of the seed. So I compute this, and I query it at the correct location where I know that the correction for ith entry sits. That is known using this function phi. Okay, so essentially this is gi of sigma plus e plus correction, which is the right value. Okay, so this is good. It will correct me the right value. What happens to the stretch? Size of the seed, we want to show that the size of the public part of the seed plus secret part of the seed, that's small. So how small they are? They are n log p for the LPN samples. The number of monomials were also n log p. Plus addition we have is the size of u and v. But remember, u and v is of dimension root m. So I'm going to get root m log p here. And this is much less than the number of output bits m. Right? So we are good here. So this is good. And security wise, we are also fine because phi, this function does not reveal any bad indices, right? It's just a computation which is oblivious of the bad set. So that's fine. Okay, so the takeaway from this is that this will correct one error. And in fact, if you were to generalize this idea, it will correct, say, m to the 0.49 errors. That's the most you can do, because in that case, we'll get m to the 0.999 dependency here. However, note that our goal is not to correct m to the 0.49 errors. We wanted to correct m lambda by L to the delta errors. This could be potentially much more than m to the 0.49. So that's our goal. So what do we do? Turns out that this idea doesn't work, but a very simple extension of this idea works. And the idea is really simple. Remember, we had m lambda by L to the delta errors. Instead of having one giant bucket of size root m cross root m, why don't I just have t small buckets? So t was the number of errors. I have t small matrices. Each matrix is of dimension L to the delta over 2 times L to the delta over 2. I'm carefully choosing the dimension so that the total number of entries in each matrix is L to the delta. And the total number of entries in all the matrix combined is m lambda. So that's much more than m. What this lets me do, this time I'm going to do the same thing. I'm going to sample two random maps, or rather assignment function. What they do, they take m output bits of the PRG and randomly place them into these bins. Okay, so this is some injective mapping, which is randomly chosen. The fact that it's randomly chosen will show up later. It's somewhat important for calculation. So we are going to sample these maps, and for convenience, just think of this maps as being two functions. There's a phi bucket, which will tell me what matrix each output index goes to. Then there is phi index, which tells me which of the index in that bucket does that output bit maps to. It will just assign the index in the matrix. So this is just for convenience. And then do the same thing. Take the correction vector. If you remember, it has t entries, non-zero. And these t entries will show in these matrix like randomly dispersed. Okay. So once I have assigned them, I want you to observe that the number of buckets we chose was t, which is exactly equal to the number of error locations.
So Aayush,
I can't hear you, Boaz. Hello? Does anyone hear me?
So basically what you're doing is m over t.
Boaz, we couldn't hear you.
So you, okay. Okay, so I'll let you continue. And
now we can hear you. Can you say that again?
So I was asking, basically, if I understand correctly, you're taking the output vector, which is of length m, and you are breaking it into t blocks, and each one of them is you're thinking of now a matrix which is square root m by square root t by square root m by square root t. And for each one of those matrices, you're doing exactly what you did before.
Exactly, that's exactly right.
So roughly speaking, you are going to somehow save something that looks like a square root of the dimension in a factor of something like square root of the dimension of these matrices.
That's exactly what you're going to save L to the delta over 2. Yes, that's precise. Okay, so he was 10 steps ahead, but let me tell you where I am. So now we have dispersed this correction vector into these matrices. Now observe the number of buckets I chose was exactly t. The number of errors was also exactly t. So in expectation, every bucket will get at most one entry. By doing more refined calculation, every bucket will, just the fact that the function is phi is random, every bucket will get at most lambda entries. You could show this with probability very high, 1 minus order of e to the minus lambda. So once you have that, which means every matrix is rank less than lambda. Every matrix has a rank less than lambda. I can do the same thing. I will factor all of these matrices, mi as ui times vi, where the dimension will be root L to the delta times lambda. Okay. And then I'm going to do exactly the same thing. I'm going to, instead of having one matrix U and V, I'm going to put T matrices, capital T matrices, UI times UI and VI in the private part of the seed, and I'll put the phi function in the index. And then same thing, GI of sigma plus error. And then I'm going, so I know that the error for ith entry sits in a matrix phi bucket of I. That's where the matrix is, and the location is phi index of I. So I'm going to compute GI of sigma plus E plus U, the corresponding U times corresponding V, and query it at index phi and index I. And then I know that this is GI of sigma plus E plus correction, which is the right value. So
why did we need the UV decomposition? Is it easy to see?
why did I use UV thing?
Yeah.
That's exactly because we want compression, and we could not put the matrix M here. But if I factor them and they are low rank matrices, I'll get compression.
And also because degree matrix multiplication is a degree 2 operation, right? So
yeah, that's
right. It fits. Yeah.
And maybe one kind of a general takeaway, which maybe people knew, but maybe people didn't know, is could be the following, right? If you're trying to encode, suppose we ignore a logarithmic term. So if you're trying to encode a sparse t sparse vector in m dimensions, then information theoretically you can do it in with only t bits. Let's ignore like the log piece part. So information theoretically you can do it with t bits. If you insisted on linear, maybe you have to use m bits. But with degree 2, you can do, I guess, the geometric average of them, square root Tm. So you can maybe not get all the way to the information theoretic, but you can get to much better than M.
That seems right. Maybe I'll take this offline to just understand formal parameters, what you're saying. Okay, so right. So this is where we were. This is good. We can correct up till the T errors, and this security wise we are fine. More crucial thing is what happens to the stretch. If you look at the private part of the seed, that's n log p, so that's fine. The number of monomials was also n log p, that's fine. The new addition is this ui and vi. So how many matrices are there? There are capital T of them. What's the size of each individual ui matrix? That's as we saw, it's lambda times L to the delta over 2, and then capital T was m lambda by L to the delta. So when you compute this product, it becomes m lambda squared by L to the delta over 2. And this is the tiny amount of saving that we're getting L to the delta over 2. That is what saves us. Just a little amount of saving. It's like L to the delta over 2 in the denominator. I think this is what Boaz was also referring, right?
Yeah, so basically I think the way
square root of the dimension.
Basically. Yes, I think that the length would be the geometric average of T and M. So ignoring the lambda thing. So if you think of T as M divided by something, then the geometric average is M divided by the square root of this something.
Yeah, okay, yeah, this is exactly what this is. Okay, so L to the delta over 2, and this is just tiny amount of savings. Turns out that's enough for getting what we want. So this, sure.
Can I ask a question? Like maybe it's a silly one, but this whole maneuver that you're doing, that this is very elegant. But I wonder, what are we trying to solve? Like, right? I mean, you had the PRG with some noise, right? A noisy version of your PRG. Is this bad? Like you're trying to correct these errors? Is it because of security or because of correctness? Or what is the problem? Because like, okay, maybe I'll let you answer and then I'll say what.
No. Okay, can you repeat your question? I'm not following very well.
I guess you were leaking. Maybe Benny is asking. Suppose you were leaking the errored PRG. Suppose you were to just not worry about core I and
correcting.
Leak out.
For example, say that I'm kind of building my PRG. You know, I have some errors, and then I do extraction, for example, over it. Right? I mean, make sure that things will still be pseudo-random even after the errors, and I still get my stretch, you know, nicely.
But so, how do you do extraction in degree 2? I mean, and you also want the outputs to be small.
Public linear functions. You have some noise, right?
You also want the outputs to be small so that you can do discrete log and take it like You also
see.
want bounded outputs.
Good. You want to remain like a 0-1 thing. Okay, you're not more working over
Just small. It doesn't have to be 0-1, but something small.
Good, good.
Yeah, it also might be an issue that the thing you will run the linear function over would be something that is large, and you don't, and that also could be a problem for you. That you cannot treat this thing that you're going to do extraction over and do a linear. Okay, maybe that's actually okay. Maybe that's not true. Maybe that's not true. Yes.
Yeah, at the end of the day, you want small output bits, and I don't know how to extract from general field elements in a low degree manner, like degree 2 bits. I don't know how to do that.
So the conclusion was this was required for to compute it rather than for security, right? To efficiency rather than security.
They're related actually. Correct computation and security, they're related to each other. If you're not correct, then you're losing security. You won't know how to argue, right?
No, but it seemed you were talking about efficiency, that you want to get the discrete log, and that's why you want the outputs to be small, rather than, I mean, that seemed like the main motivation for correcting these errors, rather than a security argument.
Yeah. When I meant correctness, I meant some other correctness, but yeah, you're right about that.
So there will be an amplification step later, you're saying?
Yeah, there will be security amplification, which Rachel roughly described, and that's fairly technical. Unfortunately, I can't cover, and we could not.
Okay.
Sounds good. Okay, so proof, I'm not going to spend time on it because it's a really simple proof. If you have LPN samples encrypting sigma and BLPRG in sigma, then we know that the output looks random, and Amit described it, so I won't spend time on it. Now, how do you, there's one caveat which I didn't tell you. We are going to lose 1 by lambda in security. Why? Because of the Markov argument we did. We had a loss of probability 1 by lambda. Therefore, we manage only to get a weakly secure SPRG. And then this picture will take you through to IO. And it builds on lots of ideas developed by the community over a few years. And Rachel's talk is an excellent reference to see that. Okay.
So Aayush, even if you manage to get not weak SPRG, you would still get weak in the next transformation, right? Because when you like add small smudging noise, so you still get good negligible security for the FE, right?
We do get negligible security. Like that depends on the proof strategy. So if
I'm saying you would still need to do, even if you manage to get the SPRG with negligible security, you would still need to do amplification, because you get like the weak cut. There are two reasons you get weak, right? One is that the SPRG has weak security, and the other is that you add small smudging noise.
So if you have small smudging, turns out there are schemes. At least there is an approach in order to get, like, use leakage amplification, leakage simulation from JP 13, and like, do you know computational leakage simulation? Like you could use that, and you can get a proof which has a negligible security loss. I can tell you offline about it. So it's just if you smudge with a polynomial amount, that doesn't mean that all the security is lost. I mean, you can still argue negligible security. It's just a different proof.
You're saying it's basically a stricter analysis, or it's a different technique altogether?
You're going to use adversary dependent proof strategies. So if you know this leakage amplification by the first paper was JP 13. Christoph and Dimitar were the authors. So you can ask me offline. I'll be happy to tell you.
All right. So this basically also explains your comment about Boaz's question, right? That if you had a good enough PRG here, gave you the 1/2 per lambda, then you could have directly got it without doing the amplification.
Yeah, that's exactly right. Okay. I mean, depends on which path you take. There's a path where you still need to do amplify again, but it's not something holy. You can always come up with a different bootstrapping. Okay, so finally, I won't spare, like, this is the last slide. Just leave you at a note of open questions. So tomorrow you are going to hear really interesting talks on an approach on how to construct provably secure post-quantum IO. Unfortunately, they are not on well-founded assumptions, but they are considerably simpler from the previous assumptions. So I'll encourage all of you to look at that. Another question is the efficiency question. If you can come up with something efficient, implementable, even from non-well-founded but simple assumptions, that will be a game changer. So it's really exciting. Finally, the last question is, can you construct IO from other assumptions, not just like what we are using, but there are many, many assumptions out there. Doesn't have to be post-quantum. Is there any other approach? That's what an open question. And with that, I'll leave the floor open to questions, and thank you for listening.
Aayush, about that post-quantum security, could you say a few words on where exactly it fails to be post-quantum?
Wait 1 second. Wait, hold on. Can we? Thank you.
Thank you, Aayush.
Thank you, everyone. Thanks. So, Amit, I can ask your question. I can answer your question offline if you ping me. Sure.
Yes, so maybe we can, people that want to stretch out, they can stretch out. Otherwise, you can also move to Gather and we can discuss more. And we'll only have a half-hour break rather than, I'm guessing many of people are, this is not their lunchtime anyway, so it doesn't really matter. And of course, you can always eat next to...
it's dinner time.
Yes, so you can bring your dinner to the computer. This is not like a usual lecture hall. So we'll see you in half an hour for Benny's talk.